turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientist. Hello, welcome to The Naked Scientist, the show that brings you the latest breakthroughs in science, technology and medicine. I'm Chris Smith, and this week your science questions are going under our microscope, including: is the universe mainly empty space? Can you win the lottery every week? Well, yes, you can. And the origins of curry, samples from 2,000 years ago, have been unearthed. Plus, when the whistle goes for half-time, we'll have a quiz for you that you at home can have a go at too. Let me introduce you to the panel of people who are going to answer your questions this week. Tony Padilla is a theoretical physicist. He's a cosmologist at the University of Nottingham and also a very popular science and maths communicator. He's made many appearances on the Numberphile YouTube channel, and he's also written a book recently. It's called Fantastic Numbers and Where to Find Them. Why are some numbers, in your view at least, a bit more fantastic than others, Tony?
Well, I just love those numbers that are sort of wild and crazy and really make you think about the most fantastic physics that are out there, the physics of black holes and the early universe and all that sort of stuff. So that's what numbers do for me. They make me think about magnificent physics.
Have you always been good at maths?
I've always liked maths. One of the stories I tell in my book is that when I first went to uni, I actually got 0 in one of my first assignments. But this was because the tutor really wanted me to sort of use a certain amount of pedantry that I wasn't comfortable with. I was actually all my arguments were right. He just didn't like how I'd laid it out on the piece of paper.
Were you studying maths at university?
I was studying maths.
You got naught.
So I think at that point I realised that I need something else from my numbers, which was physics basically, and the excitement of physics.
Because Michael Crichton, who wrote Jurassic Park, went to Harvard and was studying English to start with. And he became a bit disillusioned with the way that he said his tutors were teaching him. And he started submitting the work of some of the great masters of English. And he said in his book, if you read his book, his autobiography, he said, when Blake scored a C at Harvard, he knew English was not for me. And he retrained in medicine. And look what happened. He turned into an amazing producer of films and books and so on. So maybe you're following in Michael Crichton's footsteps.
Well, I still love numbers though, Chris. So, I haven't turned to the other side completely yet.
Also here is Emma Pomeroy, who's an archaeologist. She's at the University of Cambridge. You've joined us before, Emma, because you've told us all about your work with the Neanderthals and our early ancestors. They keep on proving themselves to be more and more like us the more we learn about them, don't they, really?
They do, and it's one of these things where the more we delve, the more we realise that perhaps, that we as humans, that we've built up to be this special, unique animal, perhaps aren't that unique, and many of our close relatives, perhaps unsurprisingly, were capable of some of the things that we do and thought were unique to us.
People always say that it's good to be married to an archaeologist because they get more interesting the older they get. Which, you don't always say that about a relationship. But when you studied, did you have a sort of Tony moment then? As in get naught on a paper that made you think in a certain way? Did you always decide, right, I'm going to go and do paleontology?
No, and actually I didn't really know. So I've ended up as a biological anthropologist. So I'm within an archaeology department, but I specifically specialise in the study of human remains and the evolution of humans. And really I didn't know that was a thing before I went to university. I knew about archaeology. I'd grown up in near Canterbury, where there's archaeology all around you, medieval city walls, and that really fired my imagination about learning about the past. And then I came to Cambridge as an undergrad quite a long time ago now and discovered this field of biological anthropology and how humans evolved, and it really just blew my mind as to how exciting that whole journey had been over the last kind of 7 million years. And so, yeah, here I am.
Thanks, Emma. Andrew Morris is a retired science teacher. He's also an author. He's a big believer in continuing education and runs science discussion groups and things like that. Joined us on the programme earlier in the year. Is the idea to get people just interested in science no matter what their background is?
Well, it started as a bit of an experiment of my own, in fact, because I'd been teaching conventional physics and maths in A levels in colleges and sixth form colleges, FE colleges. And I got more and more disillusioned with how restrictive the science is in an A-level syllabus and how far it is from what it's actually like being a scientist. So I formed the view that people switch off science at school, not really because they are unscientific or anti-scientific, I believe people remain quite curious about the world. So I started a course for people. I marketed it for people who had no science background, but who nevertheless had questions and wanted to ask about the world. It might be the natural world or the physical world. And it went really well. And it just started from their questions.
Well, who are they? Who's the they that you're talking
Very attractive to women. That's the first thing.
Why?
Who, of course, tend to be more excluded from science or dropping out of science earlier. So there's more of them.
Thanks, Andrew. Toby Wiseman, last but not least, is also he's a theoretical physicist at Imperial College. We recently asked Toby to speculate on the types of technologies that potential alien visitors might need if they were going to come and pay us a visit. That isn't actually what you do, though, is it? What do you do at Imperial College?
I work mainly on Einstein's theory of gravity in different contexts, so a lot about black holes, bit of cosmology, bit of string theory sometimes.
And was that born out of some kind of childhood trauma or a naught in an exam, or was that because you always had a particular leaning towards physics?
I think it was, there was no defining moment. I had a grandfather who was an engineer and taught me about designing things when I was very young, and I was fascinated by how things worked. And so for a long time I wanted to be an engineer, but I think over time I really just enjoyed physics and loved it. But I think it's the same wanting to know why things are the way they are. And that's sort of, I fell into it in that way.
Tony, I threw this in at the beginning because I was sufficiently intrigued to look this story up, which came out on the 31st of July, because a couple of mathematicians at another university said that they had dreamt up a way that you could always win at one form of the lottery. And they said they've got a magic number. The magic number is 27, and they've proved it's a minimum number of tickets you would need to buy to be guaranteed a prize on the national lottery. But it doesn't guarantee a profit, on the other hand. So what's the basis for this? Have you had a look at the story? Can you tell us how it works?
Yeah, I know the story. Yeah, so you have to buy 27 tickets, and if you buy 27 tickets, you will win. You won't necessarily win the jackpot, but you'll win something, maybe just the lowest prize that you can get, which is if you get two numbers. What was really impressive in what they did was that they actually were able to show that if you buy 26 tickets, you're not guaranteed. So proving that 27 is enough was actually the easy part. So you can imagine if you just bought billions of tickets, all with different.
So if I bought 100% of the tickets, I have to win, don't I?
Yeah, so I think there's something like, 40, I can't remember the exact number, 45 million, 47 million combinations or something.
Of those numbers, yeah.
Yeah, so if you bought a ticket with every single combination in, you're obviously going to win, right? That's guaranteed.
But the jackpot isn't 100% return, so therefore you still lose money.
Yeah, of course,
yeah.
Right? So, but if you can bring that number down to 27, and actually they showed using some really funky, what's called finite geometry, but it's some really cool maths, and they were able to show that actually there were 27 combinations of numbers, which will always have at least two of the numbers that appear on Saturday's draw.
So are they specific? You've got to choose certain sequences of numbers then in your 27 selection? There's
not like just one set that you have to choose. There are 27 that, in principle, of different combinations of numbers that you could choose, but they don't always have to be. You don't have to pick the same 27 as me. I could pick a different 27. We just have to sort of arrange them in a certain way. The way they actually were able to show this, they were able to package the sort of your choice of numbers into a bunch of diagrams, sort of clever diagrams. And there were 5 of these diagrams. And actually there's 6 numbers on the lottery ticket. So it was always guaranteed that you couldn't have all the numbers appearing in all the different diagrams. It always had to be one diagram which had 2 of the numbers. And that was the key to sort of winning. But the hard part was proving that 26 was not enough. Actually, the calculation for proving that 26 was not enough, in principle, should have 10 to the 165 steps, which is 1 with 165 zeros after it, which is clearly just completely impractical. There's just not enough time in the universe to do that calculation. But they used some really sort of clever software called Prolog, which was able to help them with their calculation. So that's how they proved
And
it.
when it comes down to make a profit or not, have they done any modelling to see what if you did this every week and you had your 27, what would happen at the end of a year of playing the game?
So, I mean, you're guaranteed, if you keep doing this...
You'll keep winning, but you won't necessarily win your money back each time, because it's going to cost you X amount of pounds to enter you buy your 27 entries, right?
Exactly. It costs you 54 quid to buy the 27
£2 a time.
tickets. Yeah, exactly.
And then, so do you make a profit? How often have they modelled that? So how long would you have to play the lottery that you've got a chance you're actually going to be at least cost neutral?
Yeah, that's not discussed in the paper. So I think... And I
that's
think
the key question, isn't it? I mean, what's the point of doing the research?
Well, you see, yesterday, I was telling my wife about this yesterday, and she was like, well, prove it then. I was like, what do you mean prove it? I said, they've proved it. She said, well, go out and buy 27
she
tickets.
said, shut up, Tony. I'm trying to make a phone call to buy some lottery tickets.
But I was like, but we're going to lose. We might win, but we'll ultimately lose because it's going to cost us £54, and we're very unlikely to win more than £54. So, yeah.
Toby, we had this terrific question, which I'm going to play. Just come in from one of our listeners, actually one of our overseas listeners who couldn't listen live, so she sent this to us. Have a listen to this.
Hi, Naked Scientist panel. I've got 2 parakeets. I put their cage on my balcony in Brooklyn, New York, and one day it was exceptionally windy. Yet they didn't blow off their perches. How is that? And by extension, why don't some very light humans blow away too? This is Michelle from Brooklyn, New York, a longtime listener and first-time questioner.
So there you go. Why don't her parakeets blow off their perch? I mean, they've got feathers, which means they use them to move air around and fly.
I think there's a short answer and a long answer. The short answer is that they cling on. They cling on with their feet, which are like claws, so they grab onto their perch, and by doing that, they stay. But I think it's a very interesting question, because I think we balance in quite a different way to the way they balance. So when we balance, we have to use our weight, because our feet press down on the ground and the ground presses up on our feet. The way we balance is we move our centre of gravity, where the force of gravity acts on us, to counteract any forces on us. So if the wind blows, we brace ourselves by moving into the direction of the wind. And what we're doing is we're moving our weight out over our feet to create a counter rotation to the one that the wind is imposing on us. But for a birds are very light, so they have very little weight, and so they can't do that. And presumably that's why they've evolved. One of the reasons they've evolved feet that can grip onto things, so they can exert forces by pushing and pulling, which we can't. Whether you're large or small, if the wind is strong enough, it will blow you over. So, when you jump out of a plane, if you're not wearing a parachute, or rather, if you're wearing a parachute and you choose not to open it for a while, you'll reach terminal velocity, which is about, a bit over 100 miles an hour. And that's when the wind force on you balances your weight. Because we use our weight to balance against things like the wind, once the wind gets up to sort of 100 miles an hour or so, we can't use our weight effectively. And if we're not grabbing onto something, we will get blown down.
It's The Naked Scientists with me, Chris Smith. We're answering your science questions this week, so if you'd like to have a question answered on a programme like this, don't delay, send them in via chris@thenakedscientist.com. You can also find us on Twitter, it's @nakedscientists. One of the people with us is Emma Pomeroy, who is a paleoanthropologist. You basically do archaeology of old bits of people. One of the stories that's been reasonably high in the news recently is this question about Homo naledi. Tell us about that. What is Homo naledi? Remind us who that is and why it's in the news.
So Homo naledi is really, really interesting. They're a species of human ancestor that dates to about 235 to 335 thousand years ago. So they come from one site only, called Rising Star Cave in South Africa. And they're really remarkable because actually by this point in evolution, so 300,000 years ago, we're seeing the origins of our own species, Homo sapiens. Most of our evolutionary relatives that are close to us already have quite large brains, they're quite tall, and yet Naledi has a small brain, not much bigger than a chimpanzee, quite small in terms of their stature, averaging under 5 foot. And yet there's this remarkable site at Rising Star Cave where up to 15 individuals or more have all been found deep in this really hard to access cave. And it's the only site we know them from. So this is really, really fascinating. What it does is really challenges some of our assumptions about the evolution of things like complex behaviour, so making tools, burying the dead, things like this. And the papers that have come out a couple of months ago now, there's 3 that have been published together, and they're presenting some really quite controversial new evidence from the site. And the authors are claiming that Naledi was intentionally burying their dead, that they're making tools, and even one of these burials, the individual has a stone tool clasped in their hand, and that they're also making art, so making engravings on the wall of the cave deep down in this really inaccessible place. And it's generated a lot of discussion. I mean, those suggestions that a species with such a small brain would be capable of things that we've assumed that you need a really big brain for is quite controversial. But the studies are also quite controversial because the level of evidence that's being presented to support these big claims is not as robust in the minds of many in the scientific community as perhaps it ought to be. And so this is also kind of frustrating, I think, in terms of the presentation of science, particularly in popular formats. And there's even a Netflix documentary that's just come out about this site, and there's very big claims being made, but unfortunately not big evidence at this stage.
Well, we'll watch this space. And talking of space, and thanks for that, Emma, Toby, this is a good opportunity to talk about another interesting piece of news that's surfaced fairly recently and made waves, and that was gravitational waves from black holes colliding. Who can tell us a bit more about this? Do you want to start, Toby, and then perhaps
Sure.
Tony can pick up?
Sure, absolutely. So gravitational waves are ripples in space-time that get formed when very massive objects move in a sort of, for us, an incredibly dramatic way. And so they were first observed in 2015 from a pair of black holes a billion light years away. So a billion years ago, these very massive black holes, they were many times the mass of the sun, collided with each other and set off these ripples. They travel for a billion years, and then they stretch space and time as they pass. So on Earth, this very amazing experiment called LIGO in America measured this distortion in space and time as the wave rippled past. And that was the first time these things have been seen. So since then, we've seen quite a lot of similar mergers. So we now have the technology to see that. But this new discovery in June was a completely different class of black holes producing quite different ripples. So these are supermassive black holes. Supermassive black holes live at the centres of galaxies, and they're sort of amazingly millions or even billions of times the mass of the sun. When galaxies merge, these supermassive black holes also come into orbit around each other because each galaxy will have one at its centre. They'll start orbiting and they produce a signal, and it's that that's been measured really amazingly in June.
Andrew?
Yeah, one of the things I think is really interesting about this LIGO experiment, you described these distortions in space and time, is to quantify how big that distortion is. Because I think I read that the LIGO experiment is the most extremely small disturbance is detectable over a very large distance.
Yes.
How big is it?
So for the first event discovered, it was unbelievably tiny amount. So what it does is it stretches. So you should think of a fractional change, a percentage change in length. And the percentage change in length, I think, is about a billionth of a percent. So it's an absolutely tiny. I mean, it's unbelievable that we can measure. I mean, I can't measure them. These brilliant experimental physicists have developed the technology to measure them. And it's taken decades.
But Tony, why is it important that we can even do this? Why are gravitational waves? Why did they win a Nobel Prize for Kip Thorne and others and effectively validate what Einstein was saying? Why is this useful? What sort of new vista does it open on the universe for us?
Well, it really is a new window on the universe. I mean, previously, we've looked at the universe, we've looked at the light that we see from distant stars and distant galaxies, and we can read off the behavior of the universe from that. But now we can essentially hear the universe as well, because these gravitational waves, they're traveling long distances and they're feeling the size and shape of space and time itself. So they're really a new window where we can now hear what space and time is doing.
How do we know where they've come from, though? Because if they're tiny and they're travelling just uninterrupted across the universe, when we detect them, how do we know which way they've come from?
We see the light as well, or in this case, gamma rays, so very high frequency light that we can't actually see, but we can detect. And
right. So you see a light source, and you also
yeah.
see some gravitational waves issuing from the same part of space, and you say, well, they're probably connected.
So these events can be caused not just by black holes, but also by neutron stars. And in the case of neutron stars, we will see those light signals as well, so we can detect.
But what about his supermassive black holes? How do we see that happening then?
That is very much a sort of rumbling background. So it's not so much directional. It's a rumbling background. So what we use are these special objects that are out there called pulsars. These are stars which kind of sort of, in a way, they pulsate with a very regular time interval. And what we
These
do...
are Jocelyn Bell Burnell's little green men. But they were what we thought were aliens and turned out to be stars sending out regular pulses of information.
Exactly. And those pulses, they're so regular that we can really use them to see how sort of time is changing due to the space, the distances.
So they're like
that
a
traveled.
metronome in space, and as space wobbles with the waves coming through, you can see that wobble goes off kilter, and that tells you that a gravitational wave has distorted space-time in that sort of neighbourhood.
Be expecting the pulse to come at one particular time, and if there's a slight time change, then you can sort of detect that, and that's what you're looking for. But the really interesting thing, I think, about this event, this new measurement, all the talk has been that it does come from these supermassive black holes, but this is where you can really start to test different physics, because it might not be from supermassive black holes. It might be from some really funky stuff in the early universe, right? So, for example, there can be things called phase transistors, which is where the sort of almost the properties of matter change in the early universe, and you get these bubbles of new phases forming. You can even get signals of exotic theories like string theory that are sort of imprinted on this signal, and that this signal allows us to probe that. That's why it's so exciting.
How are you going to get to the bottom of that one, Toby?
Through time. So these measurements, they've actually been measuring these pulsars, which are unbelievable objects. So they're rotating typically hundreds of times a second, and they're neutron stars. So they're the mass of the sun, giving out these pulses, but they're accurate like atomic clocks. So when you look at them over years, they hold the regularity of their pulses as well as atomic clocks. And that's what's allowed them to see these tiny distortions, and as they measure for longer and longer, they see it more accurately.
It's an amazing time to be doing science, isn't it? Andrew, let's just look at this thing that Catherine has sent in, because she wrote to say, I listened to the programme you made recently on AI. That was artificial intelligence, not artificial insemination. You'll be relieved to hear. And her question is, how do we prevent the use of AI undermining the essentials of education? As a retired educator myself, I'm very aware of the serious issues that AI is creating in schools and colleges. Already a significant number of students are using AI in America to do their homework and assignments. Will they have essential skills that are required for adult life, like common sense, she says, and problem solving and creativity? Or is it a bit like, I found that my sense of direction was definitely weakened as soon as I got a sat-nav? Are we in danger of damaging how education works in the classroom?
Yeah, my reaction to that is that that there are real risks in some areas of education, particularly if you focus on plagiarism and things like essay writing and marking and assessment. On the other hand, a lot of teachers are now getting quite interested in the possibilities of AI for improving the teaching materials that they use. There's all sorts of interesting graphical methods to represent geometry in maths, for instance. So there's a great opportunity for enhancing the materials teachers use, and there are risks. But my feeling is that it really goes to the heart of what we mean by education, the benefits of education, which in particular learning. For many people, learning is an accumulation of factual knowledge. And this can take people a long way. It can take them through exams. I even heard a story today about somebody who got 3 A's without really necessarily understanding what they were doing, but just accumulating the necessary minimal knowledge based on things like past examination papers and so on to get through exams. Whereas, of course, what we really want to achieve through learning is understanding. We want people to understand so that they can apply in novel, unpredictable situations material that they've learned, not just memorizing facts. So, of course, the kind of AI software we're talking about now is based entirely on previously written or previously drafted or music that already exists. It doesn't have creativity, it doesn't have originality, it doesn't have emotion, it doesn't, etc. And
But I guess what Catherine's saying, though, is are we effectively robbing the opportunity to have those skills from school children? It sounds to me like you're saying, well, as the machine doesn't have that, it can't replace that in people.
Yeah.
But might it make people lazy learners, as in because they don't have to go through the process of learning to get that information into their mind so they understand it and can see it from multiple viewpoints, which is what really understanding a topic is, because you don't have to go through that to regurgitate something that looks like a cogent answer. Yeah. Therefore, it could undermine your understanding, your ability to really engage with the subject.
Yeah, I agree. There is that risk, but my hope would be that it reorientates us more towards people learning to understand. So, for instance, when I used to teach, it wasn't just a matter of marking and getting percentages and preparing them to succeed in exam questions that can be almost predicted, but it was a matter of sitting around in group discussions and probing people's understanding of whether they could apply material that they'd learned to a new situation. In other words, understanding rather than just memory and knowledge.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound. Perfect music for audio and video productions.
This is The Naked Scientists with me, Chris Smith, and this week we are putting your science questions under the microscope, and with me answering them are physicists Tony Padilla and Toby Wiseman, archaeologist Emma Pomeroy and educator Andrew Morris. And temperatures have been soaring, as if I had to tell you, across most of the Northern Hemisphere as climate change bites. So this time we're asking, hot or cold? That's the thrust of our quiz. Team 1 are going to be Tony Padilla and Emma Pomeroy, and Team 2, Andrew Morris and Toby Wiseman. And round 1 is called Weighing Up the Cost of Climate Change. So, Tony and Emma, your question: Greenland has a massive ice sheet, but rising global temperatures mean it's melting. So how much ice is Greenland losing every year? Is it A, 1 cubic kilometre, B, 25 cubic kilometres, or C, 250 cubic kilometres? What do you think?
What do you reckon, Emma?
I don't know. It's a really difficult one, and it's one of these things where actually they're sort of things that are dimensions and sizes that are actually hard to conceptualise and imagine. So it sort of makes it even more difficult to answer the question, I think.
Yeah, I mean, obviously a lot of it's going to be, there'll be stuff that we don't see as well, that we underwater, so you'll naturally underestimate. So 250 cubic kilometres, let me think out. So I want to take the... Yeah, so I mean, I reckon it's that, right? Because if you think of it in terms of a distance, we'll take the cube route. So
you're the numbers guy. I am happy to go with that.
So we're going.
I'm going for that.
You're going to go C. Yeah,
that was the big one. Yeah, yeah, let's do it.
You get a ding dong. It is C. It's at least 250 cubic kilometres of water every year. That's actually 250 billion tonnes of water, give or take, or enough to fill 10 million Olympic-sized swimming pools. Measurements from space using a satellite system called GRACE weighed Greenland gravitationally to measure actually how much mass it was losing every year to find that answer. Team 2, who are Andrew and Toby, by how much are sea levels rising around the world owing to Greenland adding 250 billion cubic kilometres of water to the sea every year? Is it going up by 0.5 millimetre? Is it adding 0.5 centimetre? Or is it adding 0.5 metre to sea levels every year? What do you think?
I'd go for 0.5 metre.
I would go for... I don't think it's 0.5 metre per year.
Oh, sorry, is that per year?
I think we'd be in trouble.
So we're doing
per
year.
Last time I went to the
every
beach.
year.
No.
Per year.
So I think...
0.5 centimetre?
I would go with 0.5 millimetre personally, but I'm happy with your 0.5 centimetre.
No, we'll go with Toby, seeing as I
You're going 0.5
lost out for the
millimetre.
team last time.
0.5 millimetre.
0.5 millimetre, and you get a... Yep, you get a ding-dong for that.
Well done.
It is indeed 0.5 millimetre. The contribution of Greenland alone is adding 0.5 millimetre of sea level rise every year at the moment. Overall, sea levels are now rising at between 3 and 4 millimetres per year from all sources, including thermal expansion. So we're adding heat to the planet, and that's also making the water a bit bigger. So sea level rises just because the water itself gets bigger, even though you have not any more of it. And that's up from 2 millimetres a year annually in the 1990s. If Greenland melts completely, there's enough water locked up there to push up sea levels by 7 metres. Current estimates are that 200 million people's homes are going to be underwater at present rates within 70 years. Right, round 2 is called Ice Spy. Do you see what I did there? It's cunning, wasn't it? Team 1, back to you. Last week, scientists announced they'd brought back to life tiny 1 millimetre long worms that were found in the permafrost in Siberia. Warmed up and fed in a dish, the worms wriggled back to life and they began reproducing. But for roughly how long have they been in the deep freeze? Is it A, 4,000 years, B, 40,000 years, or C, 400,000 years? What do you think? Over to Tony and Emma.
This sounds like your thing, Emma.
Wow. Although I have to admit, I'm more usually dealing with human relative or things that are more closely related to humans than these worms. I have a feeling it was the middle one, 40,000.
Yeah, I think I did hear this story about. I can't remember the number.
You're going 40,000?
Yeah.
40,000. You get a ding for that. You are quite right. The roundworms, which were christened Panagrelamus colimaensis after the nearby Colima River where they were found, were discovered in thawing permafrost in what would have been a squirrel's burrow about 45,000 years ago. The last time they were believed to have been active. The worms break the record for the longest surviving frozen animal reanimation. Previously, a mite species that had been frozen for 24,000 years and discovered in 2021 held that title. Scientists are very concerned that rising temperatures globally will release diseases that had previously been locked away in the ice for millennia. Very good. Right, you've got to stay in the game, Team 2. Back to Andrew and Toby. We've just heard about the long spell in the deep freeze for an animal, but what about bacteria? In 2020, scientists found dormant microbes buried about 100 metres deep in mud in the South Pacific seafloor, and they brought them back to life. But at least for how long had they been locked up asleep in the mud? What do you reckon?
Are you not
Is
going
it
to
A?
give us 3?
Oh, I am.
Yes.
You're jumping the gun. You're peaking too soon, Andrew. Is it A, 200 years? Is it B, 200,000 years? Or is it C, 200 million years?
Oh, million.
That-
Bacteria
that's
are
a-
very, very early, aren't they? Yeah.
They are.
Yeah. Okay, 200,000.
200,000. And unfortunately, you get
Yeah.
no, your
It's
science
200
is off.
million, isn't it?
It's 200 million. By
Yeah,
dating the
yeah,
sediments around
yeah.
the bacteria, the team found the bacterial cells must have been away in a dormant, albeit viable state they're in for at least 100 million and quite probably 200 million years.
Yeah.
But given the right conditions again, they flourished.
Oh.
Unfortunately, you get a 0.
Oh,
you got a Tony for that answer. Round 3. So now you've got to you've got to stay and you've got to get this one right, and they've got to get it wrong to see if you can clinch this. So far the scores are: we have Team 1 on 2 points and Team 2 on 1 point so far. Round 3, the decider. Team 1, concentrations of climate change gases, chiefly CO2, are increasing in the atmosphere by about 35 billion tonnes a year. But how much of this is down to volcanoes? A, do volcanoes account for about 50 times as much greenhouse gas production as humans? B, do volcanoes and human CO2 emissions equate to about the same? Or C, do humans emit about 50 times more greenhouse gases than volcanoes? What do you think the answer to that one is, Emma and Tony?
I think volcanoes is going to be more.
Oh, I really don't know. I mean, volcanoes are one of the many things I've always wanted to learn far more about, and I haven't, so that really doesn't help us for this question.
Be late now, Emma.
Yeah.
Well, there's this Packham programme on at the moment, Chris Packham programme on at the moment, and he talks about the Great Dying, and that was caused by the volcanoes, and all this, this kind of activity. So, and I think he said it was way more than anything that we humans have produced.
Although whether that's in particular periods, I don't know.
Of course, yeah.
So
you got
go
50 volcanoes are 50 times more than us. We and volcanoes are about the same, or we emit 50 times more than a volcano. What do you think the answer is?
Volcanoes 50 times more.
Yeah, let's go with that.
Rebalancing the equation, because in fact
same.
it was C. Researchers reckon that volcanoes account for about 0.5 billion tonnes of CO2 emissions annually, which is 60 times less than we as a race are responsible for. Volcanoes also spew out sulphur particles, so eruptions paradoxically cool our planet down because the sulphur reflects sunlight back out into space. This is interesting, isn't it? So now we're level pegging, almost, if they can get this right. So it's all on this one. If you can push us to a tie-break, Team 2. Andrew and Toby, which of these places is not in the top 10 hottest places on Earth? Is it A, Jeddah in Saudi Arabia? Is it B, Basra in Iraq? Or C, Ouaga in Algeria. Which do you think is not in the top 10 places that are hottest on Earth?
I can honestly say I have no idea.
Basra is on the Gulf, isn't it? So there's some offshore winds.
Yeah, I'm happy to go for Basra.
Yeah, let's go for Basra.
Unfortunately, you get a cough for Basra. Basra is on the list. Jeddah was the answer. It's very hot, but it isn't in the top 10.
Right.
Quite a hard question, that. Do you know who the leader of the pack is? Who's right at the top there for hottest place on Earth?
Death Valley?
Yeah, you're quite right. It is. It's California's Death Valley's appropriately named Furnace Creek.
Yeah.
It's got the record for the hottest air temperature ever, which was 56.7 degrees. That was set, though, in 1913. So it just goes to show that the climate has always shown enormous departures from time to time, but we're seeing a more sustained increase now in the more modern era. Most days in Death Valley, 47 degrees is the temperature, so it's a pretty hot place to be, and the driest as well in the US. So we do have a winner. Emma, you said when you came in that you said you were awful last time on the quiz, and so you've brought it back this time.
Well, I think last time it was actually me and Andrew who were on the same team. So
are you saying Andrew is the weakest link?
No,
is that
not
what you're
at
trying
all. But I think we were both worried that we were, not going to be that we were going to be more of a hindrance than a help to our teammates. So at least we got some right this time. I think that's an improvement, right, Andrew?
Let's whip through the questions in the time we have remaining, because we've got lots of questions to get through. This one for you, Toby. Are molecules in air really travelling faster than an aeroplane, wonders Brenda, who says it's incredible they're buzzing around so fast. How can we not be aware of them? Is that true?
It is certainly true. They're buzzing around very fast. I think in the air they're buzzing around at about 1,000 miles an hour or so. Which is not that strange, because, of course, when we think about the speed of sound through air, sound waves travel through air by essentially the little molecules collectively getting together and propagating pressure waves through the air. So the speed of sound is quite closely related to the speed of the molecules actually in the air. So yes.
And why are they going so fast?
They're going so fast because they're hot, and they're very little. And the hotter they are, the faster they go.
Because there's not much to accelerate. They don't need much energy.
They don't need much energy. But I have to say, they don't go very fast in the same direction for very long. I think it's about less than a billionth of a second before they hit someone else.
Thank you for that. Andrew, over to you. Vishal says, when smoke is released by heat, it goes up, but it doesn't immediately come down. But when I throw a ball up in the air, it comes straight back. So why is that? And why does everything in the form of a gas seem to go upwards? Does gravity have a role to play here?
Yes, interesting. Smoke is a generic term. It's a lot of hot gases and particles as well, mostly soot and tar. But of course, hot gases expand and become less dense than the surroundings. So if you like, a hot gas over a fire is sort of floating on the cooler gas around, the cooler air around it, so it will rise up.
I suppose the same could be true then of water going up in the air. So if you evaporate water from the sea and it goes up in the air as water vapour and then it forms raindrops in clouds, it's being held aloft in clouds as water particles because there's rising warm air sort of pushing it up from underneath, and there's enough rising warm air to do that. So your smoke particles, it's like Toby's saying with the gas particles, the smoke particles are small enough that they're going fast enough that it doesn't take much of a nudge to keep them up there, but the ball, much heavier, stays up for longer.
I mean, I looked up some of the numbers behind what Toby has just told us. Apparently, each molecule in air is involved in a collision every 66 billionths of a metre, 66 nanometres on average. That's once every 14 billionths of a second, just as you said, right down to the billionths of a second, which means that each molecule is experiencing 7 billion collisions every second. So the image, this is the kind of thing I mean about understanding when you learn. When I was at university and learning the kinetic theory of gases, I really had no imagination of just how fast they were going, just how short. There's only 11 molecule widths between one molecule and another. So they're quite close to each other. how fast they're going and how frequently they're knocking into each other. So it's an extraordinarily dynamic thing.
Yeah, different
for
story
gas.
in space, though, and at the top of Everest,
Oh, of
isn't it, where
course,
the
yeah,
air
yeah,
is much thinner.
absolutely, yeah.
Toby?
But they're also knocking into us. And,
Yeah,
and it's not quite true that we don't feel them. That actually is the air pressure. Air pressure is precisely these tiny little things knocking into us.
Yeah.
Each one exerts almost no force at all on us as it hits
Well, I
us.
suppose,
but
as
there's so many of them.
As you drive down the road and stick your hand out the window of your car and you feel the rush of air, because your car is moving along, you're pushing a lot more atoms out of the way, and
Absolutely,
molecules, of course, and this is exerting more of a force on your hand.
And
That's drag.
Even a sound wave, low frequency sound waves, you can feel them vibrating you, and that's just these tiny little molecules bashing into you.
We're talking...
Finger on the loudspeaker of a mobile phone, you actually feel the sound waves. Incredible.
Talking of very tiny things, Tony, over to you. John says, I've read that the size of the nucleus inside an atom is comparable with a speck of dust in the Albert Hall. What proportion of what we call stuff, therefore, is nothing?
Yeah, I mean, so that statement is true. I mean, it's roughly the size of an atom is about 100,000 times bigger than the nucleus, and so that's the kind of ratios that we're talking about here. And of course, there's this. I went to see Oppenheimer last night, which was amazing.
Any good?
It was really good. I loved it. Yeah, and I was being a bit of a physics fanboy while I was watching it.
We're going to make a program all about that. So stay tuned.
Yeah. So there's a nice scene in it where Oppenheimer's talking to his future wife Kitty, and he's sort of talking about how most of what's in their hand is empty space. There's nothing there between the nucleus, the sort of electrons that are orbiting around, except of course the fields. I mean, we sort of say it's nothing, but there's actually there's the electromagnetic field that's there, and that's why when what we perceive as a solid hand or a solid table or whatever, we're really perceiving the electromagnetic field, and that's what's there. So it's not really empty. There's a field there.
Yeah. So when you press down on a surface, the reason your hand doesn't go straight through a surface, despite the fact that 99.99999% of the surface is empty space, is because my electrons around my atoms in my hand are coming close to the electrons around the atoms in the desk or whatever, and like charges repel, so the minus electrons repel the minus electrons and push back on me as hard as I'm pushing on them. Exactly.
So, and that's the field that you're feeling. But actually, what's really interesting is we can ask about actual empty space and stuff that's got nothing in it, and ask if is there really anything there? If I go out into space and I create a vacuum, is that really empty? And actually, perhaps not, because we think it has something which is called vacuum energy, which is actually the thing that's accelerating the universe. So it all comes together in one wonderful place.
Thank you for that one. It's The Naked Scientists with me, Chris Smith. We're answering your science questions this week, so if you'd like to have a question answered on a programme like this, don't delay, send them in via chris@thenakedscientist.com. You can also find us on Twitter, it's @nakedscientists. Andrew, something completely different now. We've had a question in, and it made us laugh initially, but we now really want to know the answer. So have a listen to this and tell us what you think.
Hello, Naked Scientists. This is Jeff Kirtland from Brisbane in Australia. Could you please tell me why my kitchen kettle is 1.7 litres? Is the reason something to do with physics, or is it cultural, or was it just something left over when they converted from imperial measurements to metric measurements?
I think my kettle's 1.7 as well. What's going on?
Of course, I was forced to do some research on this and Googled around, and he's quite right. Almost all kettles are 1.7 litres. So I made an inquiry with the Bosch research department.
Did you really?
Yeah, I did. Yeah. I've got the email here. Yeah. Basically, as your listener guessed, it's the nearest equivalent to 3 pints, I think it is, which is apparently 6 standard cupfuls, which is apparently the standard size of a teapot. So it is
that an SI measure? A teapot is an SI measure, is it? Or?
So apparently the kettle fits the teapot standard. Yeah, so
Brilliant.
I'm afraid there's not a lot of physics in that.
Brilliant. At least we got the answer, though. Thank you very much, Andrew. Emma, there's another question here for you, because we had a fascinating development in the world of archaeology recently, which was they've discovered traces of ancient spices on utensils unearthed in what's now Vietnam. And it's said that they have the earliest known adoption of ingredients in South Asian cuisine from 2,000 years ago in there. And this suggests perhaps an origin for curry. I love curry. Tell us more.
Yes, I love curry too. And without wanting to be sort of a bit of a kind of boring scientist and say, well, what do we mean by curry? I think it's actually important to start out and say, well, what do we mean by curry?
Chicken tikka jalfrezi made just a little bit hotter with the pilau rice and a Peshwari naan. Yep.
But so it is actually a term that we use to refer to cuisine from actually many different parts of the world, including the Caribbean, India, Southeast Asia, China, and it probably comes from sort of the 17th century and actually the British travelling out there to those parts of the world and trading and seeing food that was basically a sauce with spices containing meat and vegetables and just calling it all the same thing, a curry. But anyway,
they call it our national dish these days, don't they?
Indeed,
I think it is more popular than anything else, isn't it?
But it is really popular, and the fact that it's so widespread across many parts of the world, it makes it a really interesting question. So where did this kind of cuisine come from? So there's evidence from this site in Vietnam that you mentioned. It's from about 2,000 years ago, and it comes from samples from a sandstone slab that's probably been used for like grinding spices down. And what they do is they take these samples of the starch grains. So these are tiny particles within the plant cells, and they actually differ in their shape between different plants. So a paleobotanist can look at those down the microscope and say to you, actually, this is evidence of this particular plant, this is evidence of that particular plant. And they found a whole range of different spices, including things like turmeric, ginger, galangal, sand ginger, things that we associate with being in a curry. And there was evidence that they'd actually been ground because the starch particles were damaged. So they're saying that perhaps this is some of the earliest evidence of curry.
Can it also, apart from obviously being interesting to tell us about what people must have been eating, can it tell us a bit about trade and that kind of thing? Because if you know that some of the things they can see are, say, not native, they must have come from somewhere else. That must be a connection to another bit of the earth at the same time, arguing there was trade going on. So it unlocks the door to an understanding of what humans were doing, trading, behaving, etc. in that era.
Absolutely. And this is one of the really interesting things that comes out of the same study is that a lot of these spices that they were using, that they found evidence of, don't come locally. They're actually coming sort of hundreds of kilometres away over the sea. So it's giving us, it's not just telling us about the history of a food that we're particularly keen on, but it is telling us about those ancient trade networks. And I think it's also interesting to think about how people flavoured their food and how they enjoyed their food in the past, because perhaps we think of it as being quite utilitarian in past populations. You just ate to keep you going. And actually evidence for sort of flavouring foods and adding things like mustard to foods goes back far further than you might think. So we've got evidence perhaps even as early as sort of 40,000 years ago of people adding mustard seeds into the food, presumably to give it some flavour because they're tiny little things. So probably wouldn't have much other function.
But the standard of cuisine was also quite advanced from fairly early on, wasn't it? Because I remember it was almost 20 years ago, covering a story where researchers working in China uncovered a pot with noodles in it. And it was obviously the remains of someone's last meal. And I remember one commentator I interviewed about it said, these noodles are 2,000 years older than Jesus. But it sort of it puts it into your perspective that you think 4,000-year-old noodles, people were able to make complicated food sorts.
Absolutely. And it goes back even further. So at the site of Shanadar Cave, where I work in northern Iraqi Kurdistan, we have some evidence that Neanderthals were actually pounding particular pulses and grass seeds, soaking them perhaps to make them more digestible as well, and then kind of mushing them together into some kind of paste, which they were then cooking. So probably this kind of complex food processing goes back far further than perhaps we imagine, and go back to Shanadar kind of 70,000 years ago, and we might see something that is not too different from some of the foods that perhaps we might eat today.
Andrew, authority on all things Bosch and electrical gadgets in the kitchen. Pete says, is the electricity in our nerves the same as in our kitchen appliances, like that kettle that you were telling us about earlier?
Yeah, it's really interesting. This is a question that comes up in my discussion group about the nature of electricity. And of course, the remarkable thing that is that everything is electrical. Atoms are electrical. And the amazing fact that we live in a neutral world in which we're not, by and large, affecting each other by positive and negative charges is an amazing balance. But the intrinsic nature of atoms is that they're composed of negative and positive parts. So long when you can separate them and make either the negative or the positive part flow in a direction, you've got an electrical current, which is a source of energy. And there are many different ways in which electrical currents can occur. Now, in a metal, metals are materials in which some electrons are released from the atoms of the metal, the copper or the iron or whatever, and they become a kind of cloud of freely moving electrons. And again, when you apply a voltage across them, that drives these electrons in a current. So in our discussion, certainly when I first started thinking about nerves, we send electrical signals through nerves. Is it basically the same? And it's utterly different. It's not at all the same. But it does depend on ions. It does depend on these potassium and sodium ions in the tissue of a nerve, and the actual passage of an electrical pulse, the signal in a nerve, is simply caused by charged ions moving in and out of the cell in a kind of wave-like fashion. So it's a bit like a Mexican wave. The passage of the electrical signal down the length of a nerve is in fact due to the moving in and out of ions across the membrane of that nerve, not in any way like electrons flowing through a metal.
Over to you, Tony, because it's time for another fantastic number. One of your very popular viral videos on YouTube dedicates, you also got a chapter in your book dedicated to what's called Graham's number, which I think people would like to hear about. So tell us a bit about Graham's number.
Yeah, so Graham's number, well, for a time it was the largest number ever to have appeared in a mathematical proof. It's named after Ron Graham, who is an American mathematician. He was solving it's some mathematical problem, these kind of problems that mathematicians like to solve, very, very sort of abstract. It's in a branch of mathematics called Ramsey theory. It was involved hypercubes in extra dimensions and all sorts of wonderful things. And he was trying to find like a sort of bound for a result. So it needed to be is this thing I'm trying to find, is it less than some number? And he was able to show it was less than this number, Graham's number. But this Graham's number is just ridiculously big. It's a fantastic. So you take a number like a Google, for example, which is a 1 with 100 zeros. Well, Graham's number dwarfs that. Or take a Googleplex, which is a 1 with a Google zeros. Well, Graham's number dwarfs that. It's just off the scale enormous. You can't write it down in any kind of, well, you could in principle, but actually you would run out of space in the universe to even try and write it down. So to sort of express it, we use a special type of notation that you have to invent to describe this thing. It's called Knuth's arrows, and it's kind of like an extension of sort of powers, like powers that you learn at school, 3 squared, 3 cubed, that kind of thing. It's an extension of that allows you to very rapidly get to very, very, very big numbers. And it is. But one of the things that I discussed about it when in the videos and in the book was I was trying to think about, it's a big number, but how big is it, and how can I express that? And one of the ways I thought was, well, what if you try to imagine this number in your head? If you actually try to picture its sort of decimal expansion written out. Well, if you try to do that, Chris, then the inevitable outcome is that your head would collapse into a black hole. There's just too much information that you, long before that happened, your head, well, it'd probably, blow up. But if you manage to not blow up, it would collapse into a black hole.
So how did that guy's head not collapse into a black hole then?
Well, he used this clever notation which allowed him to compactly. He wasn't thinking of it in the decimal expansion, right? So as I said, you can imagine this. For example, let's take the number 27. I could write down 27, or I could write down 3 cubed. 3 cubed is a different way to express that number. So it's like that. But in a much more enhanced way. So he had a way of expressing it that wasn't the big, massive decimal expansion. But and so his head didn't collapse into a black hole.
Which is good, but how did it change the world, the fact that he proved this?
Well, it got in the Guinness Book of Records. That's as much as it.
That really matters.
Okay, so I think what was important about it was that it showed what was provable. So proof theory for mathematicians is a really important thing. And, understanding what's provable, what isn't provable, can you show that this can actually be answered? These are important questions in logic.
Thanks, Tony. And I'm glad my head hasn't collapsed into a black hole. Over to you, Toby. And this isn't quite a black hole, but it is blackness, the vast void space. Val says, is there nothing really there between the sun and the earth when light travels? Is it really empty, or do they not just know?
Well, space is pretty empty compared to, say, what we're used to on Earth, the atmosphere and rocks.
Has anyone actually measured it then?
People have people have measured it. I mean, so space is filled with very small amounts of matter, but there's definitely matter there. It's not a perfect vacuum.
So what if I took a metre cubed of air on the Earth's surface? How many atoms and molecules would be in that compared to if I repeated that experiment, say, out beyond the moon?
That off the top of my head, I'm not sure I can give you the answer to that. But
probably Graham's number would come into it somewhere. I think a lot
so
on the Earth's surface.
There's a lot of atoms in a metre cubed.
One atom per metre cubed in space or something.
I think it's more than that, but I think in fact, I think it is roughly about that, right? I think maybe Tony can correct me. I think it is, in fact, I think it is approximately 1 neutron or proton per metre cubed in space.
So,
I think
there's a lot
that's
of
roughly
the
average.
Sorry, Andrew. Go on. You were saying?
No, that's roughly what I recollect being as thin as that.
But I'm not completely sure it's uniformly distributed in that way. It tends to amass into clouds, so there'll be less in some regions and more in others. But in our solar system essentially has an enormous bomb at its centre, blowing up with a massive nuclear fusion reaction. That's the sun, and it is pumping out all sorts of stuff. It's pumping out radiation, it's pumping out charged particles, the solar wind. And so whilst that isn't very dense compared to the sort of densities we're used to here on Earth, there is certainly a lot of stuff in the solar system. And in fact, interestingly, I remember a couple of years ago there was that wonderful story where the Voyager spacecraft, actually left what's called the heliopause, which is actually the point where the solar wind sort of bangs into the interstellar medium, the stuff that's actually out there in deep space, and forms a sort of edge of our solar system. And so there certainly is stuff. There's not very much, but there's definitely stuff there.
Voyager very much in the news recently because NASA sent an incorrect command which had Voyager deflect its dish a bit, which put it off of alignment with the Earth signals. I think the Australians were able to use an extremely big dish, so size does matter, to send some signals, and they said they've detected the heartbeat of Voyager 2, so they think they've got it back, don't they?
How awful would you feel if that was you?
Well, no, apparently NASA obviously realised that humans make mistakes when they launch Voyager because it resets itself on axis automatically every X number of months. So they said it's all right because come October it will be back anyway. But that would be a while to wait, wouldn't it? You'd be nervous. You think, I was the guy who killed Voyager in the meantime.
It's been going for a while though.
That's all the science we have for you this week, though. Thanks for listening and thanks for sending in your questions. Thanks also to our wonderful panel, Tony Padilla. Go read his book, Fantastic Numbers and Where You Find Them. Archaeologist Emma Pomeroy, science educator Andrew Morris, and theoretical physicist Toby Wiseman. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. We're supported by Rolls-Royce. I'm Chris Smith. Thanks for listening. Until next time, goodbye.